And the very last thing we need to do is we need to study the physical pendulum. Physical pendulum is a pendulum that's made out of something that is not symmetrical, not an ignorable mass string with a weight at the bottom. So, what if we were to take a tennis racket and we were to drill a hole in the tennis racket? Now, I need to draw a tennis racket. This is great. Draw a tennis racket. This is artist's conception of a tennis racket. And we were to drill a hole right here and put a nail through that hole into the wall. Now this point right here is going to be the pivot point for our system. Now our tennis racket has an interesting shape. It also has a center of mass, which is probably going to be down here somewhere. So I'll draw the center of mass symbol. And so these two are separated by a distance, which I'm going to call x. X is the separation between the pivot point and the center of mass, wherever that is. Also, this pendulum has a moment of inertia, and I don't know what the moment of inertia of a tennis racket is. That would require either some experimentation or significant amount of calculus. Anyway, the pendulum wants to hang straight down this way. The tennis racket wants to hang, but I have deflected it to the side of distance theta. And by the same argument, the restoring torque, same argument from the last video, the restoring torque for this situation is going to be minus, okay, weight of the tennis racket times g times x times the sine of theta. Sine of theta because of the misalignment of the direction of the weight to the direction that gets you back to your equilibrium. And this, of course, is the weight of the tennis racket, and this is the lever arm because the weight of the tennis racket can be considered to be acting at its center of mass. So for this, we're going to go ahead and write down Newton's second law, and we put in our restoring torque, mgx sine alpha, and moment of inertia, well, we don't know what it is. We're going to have to measure that number, so I'm going to leave it as a number, and then alpha is d squared theta dt squared. We do the same thing. We assume small theta. By the way, people ask me, what is small theta? Since you're talking about subtracting theta cubed away from theta, anything less than half is probably considered pretty small. Now, a radian is 52 degrees, so a half of a radian is 25 degrees. Heck, let's be generous. Let's limit ourselves to 20 degrees on either side, and that's most pendulum swinging is pretty good. If you want to get it down to 1% error, then you can figure out exactly how much swinging you can tolerate. But if we assume small theta, then this changes to mgx theta equals I d squared theta. And I really screwed up here. I should have brought the I to the other side. Minus mg x over I times theta equals d squared theta dt squared. And we know how this goes. We assume a sine or a cosine. We take two derivatives and put it in here. The effect of the two derivatives is to pull out two omegas, omega squared, and a minus sign. The minus sign cancels this minus sign, and we're left with mgx over I equals omega squared, or omega for this situation must be square root of mgx over I. Slightly different bunch of things we have to measure. We have to know the distance between the center of mass and our pivot point, so we need to know where the center of mass is. We need to know the weight of the object, and we need to know its moment of inertia. This, of course, means that the period of this oscillation would be 2 pi times the square root of I divided by mgx. So let's go over here and let's just summarize what we've learned. Okay, we have learned that for the mass and spring system, that omega is the square root of k over m, something springy divided by something massy. For the torsional pendulum, omega equals square root of beta over, what was on the bottom there? I? That's right, we didn't know what I was. 1/2 ml squared or something like that. Then for the actual regular pendulum, omega was square root of L over G. No, I got that backwards. Look at me go. G over L. Recovery, everybody. And for the physical pendulum, omega was square root of I. Sorry, I did it again. mgx over I. Something springy over something massy. This is the restoring torque that brings it back. It's got the G in it. It's got the G in it. It's got the beta in it. It's got the spring constant in it. Um, Massy, resistance to motion, moment of inertia, mass. In this case, length. That's kind of weird because the masses cancel out. So this can help you find the period for all of those. We've done the process a number of times. If you don't like the 3 dots, do this for yourself once. Prove to yourself that this works. Okay, we're going to assign some homework on this, and we're going to do some things that um, ask about all kinds of different things about simple harmonic motion. This is the hardest part of simple harmonic motion is this process of using a differential equation, and this differential equation is new to us in this chapter, and it's a powerful tool. So calculus is made out of 3 pieces. They say 2, differentiation and integration, but differential equations can be considered the third part of this. Are there integral equations? Yes, there are. There are integral equations, but in general, to get rid of the integral in an integral equation, you take a derivative of both sides and you wind up with a differential equation. Little known fact. All right, so I will talk at you later.